Thank you everyone for joining us. My name is Mieszko Makuch and today I represent the InSilico Lab team, including Maciej Malawski, Joanna Kocot and Tomasz Szepieniec from AGH University of Science and Technology and ACC Cyfronet from Krakow, Poland. Today I'm going to show you our approach for workflow representation that is based on the file system directory tree, as well as some real-world usage examples from our workflow management system. Before we start off, I just wanted to run through a quick agenda. So the very first thing we'll take a look are the current workflow representations and sort of the reason why we are here, why we decided to take a new approach for workflow representation. Then we will talk about our new approach, which we call tree structure representation. And during the demo session, I will quickly introduce our workflow management system and show you how it works in practice. The next thing we'll talk about are complexity management features for tree structure representation. So things such as modularization, automated execution, and I will also show you the live demo of those functionalities, as well as some real-world usage examples. At the end, we'll talk about performance, summary of the most important features of the tree structure, as well as our plans for future releases. Okay, so let's start with some of the goals and features of today's workflow management systems. Scientific workflow paradigm is still the dominant abstraction for modeling and execution of complex computations. Workflow management systems automate management process from the design to execution phase. They mostly introduce intuitive user interfaces, integrate distributed resources, and enable sharing and collaboration on joint projects. All of this can be integrated as a web portal or suite of applications, consequently reducing the learning curve for new users. Most popular workflow representations such as DAG, TCG, UML, or PetriNet put workflow structure in the first place. And of course, from the programmer's perspective, it seems like an intuitive way to go. Users can examine application dependencies and workflow structure at a glance, and systems that supports graphical workflow editing make it even easier to create an abstract workflow structure. So, why investigate new workflow representations? As most workflow management systems put workflow structure in the first place, they usually require to build workflow specification beforehand. What we found out is that for users unacquainted with workflow abstractions, these systems can be complicated. New users may struggle to represent their experiments in the form of abstract graphs, and we think that we can design the workflow composition process to be simpler and more intuitive. So, what we can do to further reduce the learning curve and make workflow paradigm accessible to a wider range of users? Here are some ideas and hypotheses that we started with. Number 1. Put the data and applications first. Users care more about the data than abstract workflow structure. We want to give users more direct access to physical files with their visualizations, as well as applications with integrated parameter forms and output visualizations. Secondly, we want users to learn composition process through experience and analogy. To enable this, we want to reduce the number of steps required to examine results. We want to associate workflow composition process with something familiar like file system directory structure that almost everyone knows, consequently enabling users to learn by analogy. Okay, so let's take a look at our workflow representation. To address the issues that we talked about, we decided to create a workflow representation that is based on well-known file system directory structure. In our workflow management system, project organization space called workspace is in the first place. We represent applications as directories, and inputs as well as outputs are just files. Workflow structure is implicitly created on the fly as user adds and executes applications inside their workspace. Users can edit this structure by modifying the arrangement of files and directories inside their workspace. And the hierarchy between directories is used to model hierarchy between higher level workflows and lower level single applications. So let's take a look at how the simplest sequence pattern can be executed in tree structure. Keep in mind that application is a special kind of directory and files represent outputs or inputs. So file X is an initial data input used in service A. Service A produces file A that is stored in the user workspace and is updated whenever the service A is executed. Output of this service is then used as input for service B, consequently creating a sequence pattern. Okay, so now let's take a look at how the more advanced pattern, the parallel fork pattern, can be executed. So in the middle you can see the data flow structure, and on the right there is a corresponding tree structure. Here we have the file X, which is an initial file for service A, and the service A produces two output files. Those files can be used as inputs for services B and C. And finally, those services produce their outputs. So as you can see, the output files are automatically added to the directory corresponding to the given application. As I said earlier, this file is automatically updated whenever the application is executed. The important note is that although the project space is organized as a tree, workflow execution structure is independent. All of the patterns supported in DAG, as well as cycles and loops, are also supported by our model. The application input can be selected from anywhere in user space. So for example, in the cycle pattern, I can select the input B for the service A. Similarly, in the synchronous merge pattern, service C may accept multiple input files, and those files may come from anywhere in user space. So how does it work in practice? Well, our workflow management system, the ES-Epos platform, is based on the tree structure workflow representation. Now, I wanted to quickly introduce the ES-Epos platform. So ES-Epos platform is an end-to-end workflow management system designed for geophysics domain. To be precise, it is used to conduct experiments in the field of anthropogenic seismicity. So for example, shocks in mines or seismic activity linked to something like hydropower plants. And currently the system is used by over 1,000 professional users. The ES-Epos platform integrates data and applications inside the workspace, which is organized in a tree structure. It stores physical files such as inputs, outputs for applications, as well as implicit workflow structure. Workflow structure is partly defined by the way the data and applications are arranged. The ES-Epos platform utilizes distributed infrastructure with several dedicated nodes, as well as high-performance computing clusters, one of them being the Prometheus cluster, which is the most powerful cluster in our country. Now, I wanted to say a few words about the platform architecture and the technological stack. So on the bottom, you can see the resources layer with support for dedicated nodes, clusters, as well as local computing used for development. We are using the MongoDB database to store workspace metadata, workflow structure, user informations, etc. The next component is the broker component, which communicates with grid resources. There is a layer of core services with worker management, execution engine, which supports execution of single application and complex workflows, and also the workspace, which is organized in tree structure and represents experiment logic, as well as stores the files and applications. On top of that, there is a domain layer, so integration with data services, visualizations, and dedicated applications that are used for geophysics domain. The system is highly modular, so it's easy to build a platform for other domain by implementing just the domain layer. As for the technology stack, we're using Java for both backend core services, message broker, and job management. And online backend platform is based on Spring Stack. And on the front end, we are using the JWT Java to JavaScript compiler that enables us to create dynamic single-page application. Okay, so now let's see how this works in practice. During this demo, I will create a simple data flow consisting of 3 applications. So this is the interface of the online ESEPOS platform. Here you can see the workspace view. On the left, there is a workspace tree where I can store my projects. Workspace tree contains all of my files, directories, and applications. In Demo1 directory, I have one file that represents seismic events from the given location. I can quickly check the content of this file with basic parameters and location of seismic events. Now, let's use this file in one of the compatible applications. Here I can see the list of the applications that are compatible with this data type. I will choose the ground motion parameters catalog builder. Here you can see the application view with input files, controls for executing the application, as well as the output. As you can see, one of the inputs has already been selected. This application requires 2 input files, so let's add a missing input file from external data repository. I will go to data search that integrates external data repository with our portal. I will add the selected file to my project directory. Now the file is added to my workspace and the visualization is loading. After that finishes, I can move it up in the structure. Now I can select the input in the application form. We'll select the input that I've just added, but keep in mind that the input may come from anywhere inside my workspace. I will execute this application, and as you can see, the job is automatically submitted to available resources. Input files are sent to available node for processing, and after execution finishes, the results are sent back to portal application and automatically added to my workspace, as you can see here. The output visualization is displayed in the output section. Now, I can use this file for further processing. I want to filter this file, which contains seismic events, so I will use the catalog filter application. The input file has already been selected. Now in the form view, I can filter this file. Let's say I will select the events that only occurred after January 2017. I will execute this application, and once again, the outputs are added to my workspace. I can use this output for another application, in this case, GMPE calculation. I will select the parameters that I want and execute this application again. I get the basic visualization of the output, and all of the outputs are stored in my workspace. As you can see, I can create a workflow really quickly, and the system does most of the work for me. Now let's say that I want to change parameters in the catalog filter application. I will update the time, for example, to February 2017, and execute this application again. As you can see, the output file is automatically reloaded, but the application that uses this file has outdated results. So I can execute it again to update its results, but I can also use the autorun feature that will do that for me. Every time the input file changes, it will execute this application automatically. So now, when I change the parameters of the catalog filter application and execute this application, the GMP application is automatically executed as well. So the autorun can be used to execute cascade of applications. In fact, the autorun mechanism is used for automated execution of workflows, and that feature I will show you later on. Now, I wanted to show you some of the complexity management features that we have implemented on our platform. We've achieved workflow modularization and a hierarchy using part-whole hierarchies between directories in the user workspace. User can merge directory with applications or sub-workflows to create a higher-level workflow. As a result, directory is replaced with single higher-level application that aggregates inner applications. To facilitate composition process, this action is easily revertible, so users can create workflow by trial and error. Here is an example of directory that was merged into workflow. Service A directory, which is also an application, consists of two other applications. After merging it to workflow, the directory is replaced with single application that encapsulates the internal structure. The inputs of the workflow are files that were coming from outside the merged directory. So in this case, it is a file X. Outputs are customizable, so users can decide which outputs of the internal applications are exposed. Another thing that I wanted to show you is the workflow view that is created by aggregating the application views that are inside this workflow. Here we have a view of a sample application. Let's say that our workflow consists of 3 applications, and here we can see their views. We are extracting individual components from those views to create a single workflow view. The workflow view is dynamic and customizable. Workflow designer can choose which forms are visible and which should be treated as constants and remain hidden. User can also decide which outputs are visible. The next thing is the workflow execution engine that can execute individual applications on demand, autorun individual applications, and also execute workflows consisting of multiple applications with support for both on-demand and automatic execution. Service Executor executes single applications on demand. It collects inputs from the user space and sends it for calculation to Worker Manager. Received outputs are added to the workspace, and the user can examine the results. Autorun uses events in user workspace, such as event about new files, tree structure modifications, to execute given application whenever the input file changes. Finally, the workflow executor uses Autorun to execute workflows consisting of multiple applications. Here you can see the workflow organization in the user's workspace and implicit workflow execution structure that is based on connections between applications. In the database, we only store connections between applications and their inputs. There is no need to build or analyze the graph. Workflow execution engines support 2 models of execution. First, on-demand workflow execution executes the whole workflow whenever the user wants to. Second, automatically executes all the services that were affected by the input change. Okay, so let's see how it works in practice. During this demo, I will show you the merge workflow action and other complexity management features. At the end, I will also demonstrate some real-world use cases. So again, this is my workspace view. I'm going to use the set of applications that we created in the first demo to show you merge workflow action. I can match this directory to workflow using merge workflow button. Now I can see the workflow view. Let's go to workflow editing and customize this view. Here I can give my workflow a description. I can replace default application names with something more useful. And then I can customize the forms Let's say that I want to have catalog filter forms hidden and GMP calculation form exposed and editable. At the end, I can choose which outputs are visible. Let's say that I want only the outputs from the last application to be visible. Okay, I will save the workflow view and workflow is ready to use. I can execute the workflow using a single button and all of the application will be executed in the correct order. Under the hood, system enables auto-run mechanism that I showed you in the previous demo to execute when the inputs are ready. At the end, I get visualizations of selected inputs, and outputs are also visible in my workspace. Now, in order to reuse this workflow, I can, for example, copy it to another place. Let's copy it to my root directory. The system copies the whole workflow with files, applications, their input, and their parameters. The workflow merge action is revertible, so I can easily expand this workflow and edit the inner structure. I can also share this workflow with my colleague using the share button. If he has an account on the ES-Epos platform, he will be able to copy this workflow to his workspace and use it or make the necessary adjustments. Lastly, I wanted to show you some more complex workflows that are real-world use cases. And the first workflow is an extension to the toy example that I showed you in the first part. It contains of 7 applications and is used to calculate full GMPE model. As you can see, it has much more complex visualizations. And also, after expanding it, you'll see that it has much more complex structure. So it contains of, as I said, of 7 applications. And in this case, the ability to merge it into single workflow application is quite useful. Next, we have a workflow that is used for visualization purposes. It is used to display events with relatively high magnitude, as well as seismic network with seismic stations. In this case, we are using data from seismic network located near the hydro plants in 2 locations in Vietnam. So I can see the seismic network around the hydro plant, as well as the events that occurred near it. Moving towards the end, I wanted to quickly show you the performance results of execution. During tests, the ES-Epos platform was running on our development instance with 3 dedicated computing nodes. It was able to execute up to 120 services in around 5.5 minutes. The main limitation here was the graphical user interface. The web UI supports all screen resolutions from desktops to smartphones. Summarizing, today I've showed you our workflow representation based on directory tree structure. Its main goals were to put data, applications, and visualizations on the first place, as well as to reduce the number of steps required to create a workflow, consequently enabling users to quickly test their ideas and learn workflow composition by experience. We've associated composition with directory tree structure that almost everyone is familiar with. We think that this approach for workflow representation could be especially appreciated by users unacquainted with workflow paradigm. We also think that the best results can be achieved in end-to-end systems with rich presentation layers that are designed for specific domain. At the end, it's worth noting that although user space is organized in a tree, the workflow structure is not restricted as it can support cycles or workflows with multiple starting points. As for the future, we are planning to provide some other visualizations of the data flow to help users examine complex workflow dependencies. Also, we plan to optimize Web UI to support larger workflows. At the end, I wanted to thank the EPOS.pl project, which enables us to expand and maintain the ES-Epos platform, as well as scientists from EGPAST for valuable comments on new functionalities. The ES-Epos platform is available at the following link, and the registration is free of charge, so you can try it today. Thank you once again for joining us today. Everyone take care and have a great day.